In this lecture, we're going to discuss the three different types of linear defects, or which we call dislocations. And after we learned or defined the three different types of dislocations, the edge dislocation, screw dislocation, and a mixture of the two, mixed dislocation, we should be able to describe and make a drawing of the dislocations, and note the location of the dislocation line, and indicate the direction along which the dislocation line extends. And also, we're going to describe the atomic structure within the vicinity of a grain boundary, which is the interfacial defect. A dislocation is a linear or 1D defect around which some of the atoms are misaligned. Dislocations are present in all materials, not only in metals, but also in ceramics and polymers. They are especially useful in explaining deformation and strengthening in metallic materials, which we will learn later. And there are three types of dislocations. They are the screw dislocation, the edge dislocation, and a mixture of the two, which we call the mixed dislocation. So next, we're going to take a look at each of the three types of dislocations. An edge dislocation is an actual half plane of atoms inserted in a crystal structure. So this actual half plane terminates or stops within the crystal, right here in this case. And this is termed as the edge dislocation. It is a linear defect that centers on the line that is defined along the end of the actual half plane of atoms. So again, if you take a look, this half plane atom stops here within the crystal structure, and we use edge dislocation line to represent the location of this dislocation. So this edge dislocation line extends along the end of the actual half plane of atoms. So in this figure, the atom here, the bottom one I'm showing here, is one atom from this dislocation line. So this array of atoms that goes into the screen or into the page forms the dislocation line. Okay, so it goes into the screen. So if we use a symbol, it will look like that. Okay, extends all the way back into the screen, if we say so. So this line is perpendicular to the plane of the page. So that's, again, one atom from this row of atoms, and is the edge dislocation line. And the edge dislocation is represented by this symbol, looks like a perpendicular sign. So that's the edge dislocation symbol, but only for if the actual half plane is on the top portion. So this vertical line indicates the actual half plane, and the horizontal line indicates the plane of atoms this half plane stops at. But in some other cases, we may see an edge dislocation on the bottom portion of the crystal structure. Something look like, for example, look like this. We have another actual half plane of atoms, but it's on the bottom portion of the crystal. In that case, we are going to use a symbol in the opposite orientation like that. So again, the vertical line part of this symbol indicates the actual half plane of atoms, and this horizontal line representing where this half plane stops within the crystal structure. So we can see within the region around the dislocation line, there is some localized lattice distortion. The atoms above the dislocation line are squeezed together, and those below are pulled apart. And this is reflected by the slight curvature of the vertical planes of atoms as they bend around this actual half plane. In this section of crystal, you can observe a schematic depiction of an edge dislocation. Right now, I didn't insert the edge dislocation yet, which is an actual half plane of atoms. So without the actual half plane of atoms, the crystal or the other atoms, this is the perfect crystal or atom arrangement. Now let's insert an actual half plane of atoms, which is highlighted in yellow. So this actual half plane of atoms is the edge dislocation, which causes distortion at its surroundings. And the edge dislocation line is defined, or it's defined along the end of the actual half plane of atoms. So now if we look from this direction, it's perpendicular, is starting from the bottom, the third yellow atom, and goes all the way into the board, is perpendicular to this plane. But if I rotate it in another orientation, you can see this line now, the yellow line, okay? Again, the bottom row of atoms indicating the edge dislocation line. But if usually the view for a 2D view, when we draw the edge dislocation, is just in this direction. We look from this direction, so it's perpendicular to the plane in this orientation. And let's do something. You can see this edge dislocation, or the actual half plane of atoms, actually is not staying there forever. In fact, it can move. And this is the mechanism of plastic deformation. Okay, plastic deformation means permanent deformation is because of the movement of the edge dislocation. So for example, if you bend a piece of metal, why is bending? Why is deformed? Is because when we push this edge dislocation all the way to the surface of the material, you can see there is a step formed, right, at the surface or outside of the material, and this is the deformation. The magnitude and direction of the lattice distortion associated with a dislocation are expressed in terms of a Burgers vector, which is denoted by B. So this is the vector B, or Burgers vector B, which is used along with the edge dislocation symbol to fully describe the edge dislocation. And it is also used with the screw dislocation to describe these one screw dislocation. We'll see that later. So the Burgers vector indicates the magnitude and direction of the lattice distortion. How do we figure out the Burgers vector then? Well, to find the Burgers vector, and we say it is required to close a loop of equal atom spacings around the edge dislocation. So we are gonna construct a loop or draw a loop along the lattice edges and around the edge dislocation. You will see, and then we need to close the loop. Usually if there is a dislocation, the loop is not closed. So another note is this loop is not a circle. Usually when we say a loop, it's like a circle, but this one is a loop around more like a rectangular loop. Okay, so let's draw a loop now starting from this one atom. You can start from any atom, okay, any random atom. So we start from this one on the surface. It's not on the surface, but it's on the top row. And take equal atom spacings. So I'm going to take 4 atom spacings to the right first. 1, 2, 3, 4. And then take 4 atom spacings down. 1, 2, 3, 4. And change direction and walk back to the right or to the left. 1, 2, 3, 4. And lastly, gonna walk back up 4 steps as well. 1, 2, 3, 4. Now you can see because of the edge dislocation, this loop is not closed if we take equal atom spacings around it. And this Burgers vector is used to close this loop. So if we call this point is the start and this is the finish, and Burgers vector is when we connect the finish to the start, and this will be the Burgers vector. Well, another question is, when I draw the loop, I'm taking the steps, or this loop is a clockwise loop, right? Why did I take a clockwise? Why didn't I go counterclockwise? Well, actually you can go counterclockwise as long as you keep consistent throughout your problem. If you have one crystal structure, but you have different dislocations, as long as all of the dislocations follow the same convention, then it's fine. But here I'm using one convention, which is the right hand rule, and from finish to start. Okay, so the right hand rule actually is applied in a lot of different fields in engineering, right? In engineering classes. So here, to apply the right-hand rule, we first figure out the direction of this edge dislocation line. And since this edge dislocation line is going into the plane, so it's pointing into the plane, and we're going to use your right hand to grip this direction, pointing into the direction of this dislocation line, and your thumb points to the direction of this dislocation line, and the direction of your 4 fingers curve in the direction of this loop. Okay, so it's curved clockwise in this example. Pointing your thumb into the direction of the dislocation line, and your other 4 fingers will curve in the direction of your loop. And then you just follow this direction to take the equal atom spacings loop. And your final step is to close the loop from finish to start, and that will be the direction of the Burgers vector. And we can also see that the Burgers vector of the edge dislocation is perpendicular to the dislocation line. Let me clear this a little bit. So we said the dislocation line is pointing into the board or into the plane, and Burgers vector is within this plane. So Burgers vector goes, the dislocation goes in, therefore it's perpendicular to the dislocation line of the edge dislocation. Another type of dislocation is called screw dislocation, which may be thought of as being formed by a shear stress that is applied to produce the distortion, which is shown in these figures. Figure A, we have a perfect crystal, and if we cut into this crystal halfway through, not all the way to half, but halfway through, and we will apply shear stress to the left. We push the left part of the crystal up by 1 atomic distance, and this will result distortion, and this kind of distortion is called screw dislocation. So here in figure C, we can see the screw dislocation, or we can see a better view for the left portion of the crystal is shifted 1 atomic distance up relative to the right portion or right hand region of the crystal. And the atomic distortion associated with a screw dislocation is also linear and along this dislocation line. So in this figure C, the dislocation line is this line. It's a linear line, which is resulted from the line here. If we cut halfway through it and we shear along this line, and this will be the screw dislocation line. The screw dislocation, the name derives from the spiral or helical path or ramp that is traced around the dislocation line by atomic planes of atoms, which is hard to draw on this figure, but we can draw one path. By the way, also we can show this Burger's vector. Okay, so if we take the same or equal atom space and to draw a loop around this screw dislocation, we can start from this point. Take 4 steps again. 1, 2, 3, 4, and change the direction. 1, 2, 3, 4, and change direction. 1, 2, 3, 4, and then go all the way back. 1, 2, 3, 4, and this Burger's vector is used to close the loop. So again, now you can see this loop is not within one plane, but here is kind of a ramp, right? Goes from top, goes down. So that's where the name screw dislocation comes from. So again, the line along which shearing occurs is the screw dislocation line, is still a linear line. And the symbol we use for screw dislocations is kind of this this curvy line or a circle go around the screw dislocation, kind of like the moment vector symbol. So if this screw dislocation points up and use your right hand rule, we draw the screw dislocation symbol like this. So this is a 3D model for one crystal section. This is a crystal without a screw dislocation. Now, if we introduce a screw dislocation by applying shear stress on the top portion of this crystal, and this is what happens. So the top region of the crystal is shifted to the right by 1 atomic distance. You can see this, right? So the top region is shifted to the right relative to the bottom portion, and those displaced atoms are highlighted in yellow, and those atoms are around the screw dislocation line. So if we change the orientation of the crystal, and that line is kind of the line between the 2 rows of yellow atoms, but going all the way into the board. So it is a linear line. Take another look on the screw dislocations. So the dislocation line is along the shearing line, and we use this symbol to indicating the screw dislocation line. And again, we use right hand rule to figure out the direction of the rotation. So in this case, we use your thumb to point into the crystal structure, since the line is extending back all the way into the plane. So our thumb will point into the plane, and the direction of your 4 fingers will curve in the direction of the screw dislocation symbol, like that. And again, we use Burger's vector to indicate the magnitude and the direction of the distortion. So this Burger's vector, we use the same method as before, is required to close the loop of equal atom spacings around the screw dislocation. And here is the top view of the screw dislocation. So the dislocation line is the line AB here. and Burgers vector is here. So we can see the relation of the Burgers vector and the dislocation line is parallel. So for screw dislocation, the Burgers vector B is parallel to the dislocation line. Most dislocations found in crystalline materials are probably neither pure edge nor pure screw, but exhibit components of both types, and these are termed mixed dislocations. So all three dislocation types are represented schematically in the following figure. So at point B on this surface, we have a pure edge dislocation. And this is the edge dislocation with the symbol, and the Burgers vector is perpendicular to the edge dislocation line, which is going into the plane. And at point A, here, and dislocation is pure screw dislocation. But for the regions in between, where there is curvature in the dislocation line, the character is mixed edge and screw. So the lattice distortion that is produced away from the two faces is mixed, having varying degrees of screw and edge character. Let's summarize dislocations. Dislocations are one-dimensional defects around which atoms are misaligned, and we use Burgers vector B to measure the magnitude and direction of the distortion around dislocations. So for metallic materials, Burgers vector for a dislocation will point in a close-packed direction. So think about the close-packed direction in BCC structure, which is the 111 direction, and close-packed direction in FCC structure is the 110 direction. And the magnitude is equal to the interatomic spacing. And since along the close-packed direction, atoms are touching each other, so the interatomic spacing will be 2r. So now we know how to the magnitude and the direction of the Burgers vector for a given crystal structure. So for edge dislocation, it's actual half plane of atoms inserted in a crystal structure. The Burgers vector is perpendicular to the dislocation line. For screw dislocation, which is spiral planar ramp resulting from shear deformation, and the Burgers vector is parallel to the dislocation line. For mixed dislocation, the Burgers vector is neither perpendicular nor parallel for mixed dislocation. In 2D, we have interfacial or planar defects. Interfacial or planar defects are boundaries that have two dimensions and normally separate regions of the materials that have different crystal structures or crystallographic orientations. So those planar defects including external surfaces, grain boundaries, twin boundaries, stacking faults, and face boundaries. But in this chapter, we will focus on grain boundaries. So let's review a couple of vocabularies to describe grain boundaries. So we will learn the crystal structure. We say we have grains in multicrystalline structures. So grain is one of the crystals having the same crystallographic orientation in a polycrystalline material. So grain boundary, by its meaning, is the boundary between the adjacent grains, and it is a surface defect. A grain boundary is represented schematically from an atomic perspective in figure A. So we can see the atoms near the boundaries of the three grains do not have an equilibrium spacing or arrangement, and also different grains have a very different orientation. So those grain boundaries are very clear or easy to identify. They are the boundaries between different grains. And figure B is the image from a stainless steel sample under microscopy. And again, the grain boundaries are very clear because of different orientation, and the colors for different grains in the image are slightly different, or the darkness is slightly different. So we can see the grain boundaries very clear in this figure.